Greetings, everybody. Welcome to our new week of classes. We're going to be starting this week by ending with some fundamental information. So, in this video, I'm going to discuss some basic signal examples. And what do I mean by that? When we are studying systems, okay, let's say we have a model of differential equations or a transfer function that I'm going to discuss later. What I want to do is study how this system will behave under a specific set of inputs. So for that matter, we have a couple of very basic input type signals, and we are using them and feeding them into the system in order to evaluate how it will behave. So this is what we're going to explain, as well as some additional information. One of the most basic types of signals is the step input. Okay, so what is a step input? It is basically a switch going on at time zero, where the signal switches from zero value to the value of one. Okay, so it's a fixed, stable value of one for all time. Okay, simple as that. So this is uh, the step input. Okay, at time zero. So what do we use the system for? Okay, we are using this system because it symbolizes a static or a stable force or any type of energy being fed into a system. Okay, so we are using this as an input in order to be able to understand and evaluate if the system, and especially an automatic control system, will be able to follow a fixed input. So let's say I'm feeding the system with some sort of fixed command, like a fixed speed or a fixed position or a fixed temperature or a fixed pressure. Okay, and I want to evaluate if the system is going to be able to reach this goal. Okay, so if our goal here is this step signal, will the system be able to reach it, or will we have an error? Will it reach it fast uh, and stay there? Will it reach it by having some sort of short oscillation, or maybe an even higher and undesired oscillation, right? So how are we going to evaluate if the system is in a position to reach a fixed state? We are going to provide it with a fixed input, a step input, right? So let me also note that in this situation, the output of the system, usually in control systems, the output is called the response. Okay, so in this case, it is called the step response. Okay, so when you hear we are evaluating the step response of a system, we mean that we are actually measuring the output under a step input, right? And of course, since it is works, like a switch, it has this sort of very nice property. If you multiply it with any other function, it pretty much cuts the function off for negative time, right? So this is an example, as I mentioned earlier, of a step input. And this is what happens if I have a function right here. If I multiply it with a step input, it cuts it off at zero. And this is very useful because later we can use this sort of step function in order to, define specific input signals. So this is the first basic input. Okay. Of course, we can do various, variations and modifications to it. For example, the time shift. The time shift is a very simple modification of the step signal. We pretty much move it in time by t0 seconds. Okay, so if here we have this t0, the step input moves from switching at 0 to switching at t0 seconds, right? A very simple modification of the step input. Now, another variation of the step input is the rectangular pulse. So what is it basically? It's the difference between two different step inputs, and it is very simply a signal that is a step input, but on a fixed interval. Okay, so for example, this sort of difference here from these two delayed step signals is basically a pulse, I'm sorry, that starts at time 0, okay, and ends at time 3. So this simple uh, pulse here, oops, I'm sorry, is an example of a rectangular pulse. Okay, and you can again use this to define and make different signal combinations. Okay, so this is an example of a delayed step input. It starts actually 2 seconds earlier. And this is again the multiplication of a function f by a pulse with duration, 3 seconds. Now, the second basic input is the ramp function. Okay, it's again, I would say, it's one step ahead from the step input because it represents a steadily increasing command. Okay, so we may use a ramp function to model how a system will behave when we are providing it with a steadily increasing energy and measure if the system will be able to follow this sort of increasing command. Okay, so it's simply, as the title says, a ramp function. So, okay, it goes like that. I'm sorry, let's make it a little bit better this way. And what it simply denotes is, when we input a system with a ramp function, we can see if the output of the system will be able to follow or not follow the ramp input. So in the ideal situation, we may have this sort of fixed error. I'm sorry, but my hand, is juggling a bit. Or in an ideal situation, we may be able to follow exactly the ramp input. Okay. And also, for that matter, the derivative of the ramp function is actually the step input. So that's why I said it is one step further from the step command, right? So this is why we usually model systems using the ramp function, because it is ideal for measuring the steady state error from an increasing command, from a steadily increasing command. Okay. And these, of course, are the several variations that you can do with the ramp function, okay? Just like the step function, okay? So you can delay it in time. For example, here we have delayed the ramp by 2 seconds. And again, we can multiply it with a pulse to have a ramp input, but on a very specific time interval. Now, the next very important function is the impulse function, okay? It's actually very, very famous. Now, what is the impulse function? Okay, the output for this is, command is called, for this input, I'm sorry, is called the impulse response. You may have heard that from other courses. Now, the impulse function represents pulse, obviously, which means that we have a signal of very, very high intensity, but it is provided in a very, very short time. Okay, if I could provide you with a measurement of an estimation for this, think of a rectangular area right here, as you see. Okay, the basis is 1 over epsilon, and the height is epsilon. Okay, so the whole area is 1, has a value of 1. But think what happens when epsilon becomes higher. For low values of epsilon, we are providing, let's say, low energy to the system over a very large interval close to 0. Okay, but as epsilon becomes higher and higher, we are providing more energy to the system on a shorter interval. Okay, and as epsilon becomes more and more and more high, we actually provide a lot of energy to the system. So this rectangle here, this rectangular area becomes very, very high. So we're providing very high energy to the system, but on a very, very short interval. So we are using this input in order to understand how the system will behave under very abrupt input changes. Okay, so let's say, for example, we are having an electrical circuit and we are having a very abrupt switch open and close. Or let's say we have a mechanical system and at time 0, I go and I punch it with all my power, right? So that's an impulse input. Okay. So this is a very, very important uh, input for modeling. And also you may see in some books this note right here. We used to say that the impulse function is actually the derivative of the step input, because the step input is a switch that goes from 0 to 1 at 0 time, so it has a discontinuity, and we can say that this discontinuity, this derivative that is very abrupt, is actually what it used to model the impulse function. Okay, so an example of impulse response is this case. We have a spring mass, a double mass actually model. This can model, for example, a car. So this here is the mass of the car when where we are sitting. And what happens when we are driving down a road and we see a very huge bump, the model will go very abruptly, very high up, and then go back down. So this is the impulse response in a mechanical system, right? So ideally, if the model is behaving desirably, we should have, a very lower oscillation, right? So in an ideal situation, the oscillation would be much, much lower, or maybe even lower if the car has a very good suspension system, right? So how do we model this behavior? By providing an impulse input to the system, right? So these are actually all the basic types of inputs, okay? Step input, ramp input, and impulse input. Of course, we may also use a paraboloid input. This is practically an input that changes and increases quadratically in time, and study whether the input of the system will be able to follow it, maybe with a fixed error like that, so the error here is fixed, or maybe model be able to follow it ideally and stay exactly on the desired input, or in the bad situation, deviate completely and go to infinity. So, of course, this is a much more difficult problem because here the input is increasing in a quadratic manner. So following it is much, much more difficult. So these are the basic input signals that we'll use in modeling or not only mechanical systems, but any type of system. Now, in addition to those signals, during our automatic control course, where we are going to solve differential equations and study differential equations, we are going to come across some specific sets of signals, okay, some specific sets of functions. These functions are very common because these are functions that are used when, solving differential equations. So you are going to come across them. So let's discuss about them a little bit. One of the most common functions that you will find when solving differential equations is this exponential function that you see right here. Okay, e exponential to the a times t. And of course, this function will behave completely different based on the value of alpha. Okay, so let me here plot this complex plane. Okay, so here this is the real value, the real part of an argument. Here is the imaginary. And let's study what will happen into this function for different values of alpha. Okay, so let's say alpha here is positive. Okay, uh, any value that may be, of course, a real function, a real value, but on the positive side. Okay. In this situation, this term obviously is epsilon to the alpha, which is positive, okay, multiplied by the time. So in this situation, this function will be unstable. Obviously, as time increases, this function will go to infinity, right? So when alpha here is positive, this function will lead the system into instability, right? Okay. This is a bad situation that we generally want to avoid. Now, for the, in between case where alpha is exactly 0, what will we have? We will have epsilon to the 0, which will give us the value of 1. So in this case, which is actually the threshold between stability and instability, epsilon to the 0 will be a stable value equal to 1. Okay, basically we will obtain the step input. Right? So what's more important is what happens when alpha is negative, right? So let's go here, for example, epsilon to the minus stuff. Okay, obviously this is equal to 1 over epsilon to the t, where t is time. Okay, so how does that function behave? As you may remember, of course, since the denominator goes to infinity, this whole function goes to 0. Okay, so for values that alpha is negative, this function will steadily but surely go to 0 without having an oscillation though, right? So no oscillations here. And this is the desired case. We generally want to obtain when solving a system values like that are negative, that get us to 0. And more importantly, what will happen for alpha that goes more and more and more to the left of the complex plane? So what will happen when alpha is equal to minus 2? We will have epsilon right, to the minus 2t, which again goes to 0, but let's compare it to the previous case. Okay, since alpha now is more left on the plane, so by absolute value is higher, the denominator here is 1 over epsilon to the 2t. So the denominator here goes to 0 even faster. So this function now will go to 0, but it will converge to 0 at a much higher rate. Okay, and then this will happen again the further we go on the left. Epsilon to the minus 3, again it will go to 0, but much faster. Epsilon to the minus 4. Okay, let's say we have epsilon to the minus 100. Okay, this will be a function that goes to 0 at a much higher rate. So we will obtain a much faster convergence. Okay, so one thing to remember here, the further you go on the left, okay, the faster you will converge to the 0 value. This is extremely important when analyzing control systems, right? More left, faster convergence to 0. Okay, and when I say more left, I mean that alpha becomes, more and more and more negative. So this is a very big category of functions that we are going to see next. And the second big category is this modification right here, where you have an exponential function, right, multiplied by a cosine function, right? So what do we have here? Let's think about it. We have a cosine signal, and the cosine signal, as you know, is periodic, and it oscillates, right? And we have an exponential function, epsilon to the a. Okay, so let's think about it. Let me draw the complex plane again. Okay, so let's think about it. What will happen when alpha is positive? Let me draw this situation right here. When alpha is positive, okay, we will have a term, I'm sorry, that oscillates and a term that goes to infinity. So we will obtain an oscillation that becomes higher and higher and higher and higher. So we will obtain something like that, okay? So we will obtain this sort of oscillation where the system, of course, will end up destroying itself because it goes to infinity, right? So this is an undesired case. Again, when the alpha is positive, we go into instability. All right, cool. Now, in the threshold situation where alpha is exactly 0, okay, this will be epsilon to the 0, so 1, multiplied by the cosine signal. So in this case, we will obtain an oscillation that is stable. What I mean by that, it doesn't go to 0, it doesn't go to infinity. So in this situation, I'm going to draw this here, we will obtain this sort of stable oscillation, right? So the system will be stable, I'm sorry, the function will be stable, but it will never go towards 0, right? So this is the threshold situation. And again, what happens when we go here towards negative values of alpha? Then we will obtain a cosine signal, so an oscillating signal, multiplied by epsilon to the alpha tau. Alpha is negative now, so this signal goes to 0. This function goes to 0. So their multiplication will give us an oscillation that becomes shorter and shorter and shorter until it completely diminishes. And this is the situation right here. We have an oscillation, we have a cosine signal that becomes slower and slower and slower until it reaches 0. Okay. And of course, similarly to the previous case, not the higher, I'm sorry, the lefter, I'm sorry for this bad English expression, the more left we go on the complex plane, okay, this means that this term will diminish much faster. So this means that the oscillation will converge faster to 0, right? So the more on the left that we go, okay, this oscillation will converge much faster. So it will go to a very uh, left in the complex plane. Let's say we go to minus 10 or minus 50 or minus 100, then we will obtain oscillation that will go very fast towards 0, right? So this is what happens when we combine exponential terms with cosine terms. Okay, when the exponential function is stable, we obtain a diminishing oscillation. Okay, so this is very common in mechanical systems, for example, and for that matter, for any other type of system. So, pretty much this is all I wanted to say regarding basic inputs and basic functions that you are going to come across. And one of the things that we used to do in previous courses in automatic control, especially when I was a student at the mathematics department, is that we used to use all of these previous signals in order to construct signals of our own. So what we would probably do, for example, let's say we want to give a description for this type of signal, we would usually break it down into segments. Okay, so we have these segments right here. We would model each function. So for example, this function, for example, is 2 taf. Okay, this is 2 by the u, right? And this is another linear function that I can actually easily compute. And what we would do is multiply each of these functions by a pulse. So this is a pulse from 0 to 1. This is a pulse from 1 to 3. This is a pulse from 3 to 4. And then add all of these signals together to obtain a closed form description for this complex signal. But this is not much common nowadays. We don't really do that. So I'm not going to spend a lot of time describing this situation, this process. So in our next course, we're gonna go deep into the main topic of the automatic control systems, and we are gonna start by describing a solution of a system using transfer function. I'm sorry, using transfer function and Laplace transforms. And any question that you have, write them down in the comments, and I will reply, of course. So thank you very much. Okay, I'll see you in our next video.